All right, everybody. In this video, we're going to cover 10.1, and so that's talking about two sample t-tests and two sample t-intervals. It has to do with comparing a mean among two groups or finding a difference in means among two groups of data. So again, our notes go out of order, the homework goes out of order. We first did 10.3 out of the textbook, which dealt with proportions. Now we're going to handle the means. So again, what we're looking at is, and all these notes are half filled in, we're just going back and doing all the mean stuff we skipped over in the last video. But we are looking at doing a two-sample t-interval and a two-sample t-test. Remember, most of the time when you're dealing with means, you do not know the population standard deviation. You only know the sample standard deviation, usually. And so that forces us to use t-statistics as opposed to z-statistics. Okay, so we're looking at t-intervals and t-tests. All right, so here are some examples of scenarios that may come up. Are IQ scores for people who attend college different from those who do not attend college? All right, so the average IQ score or the mean IQ score among those two groups, are they different? How much taller are men on average compared to women? So again, these aren't proportions or percentages, they're an average number. And so it's comparing the difference of averages between two groups. So let's skip over this. We did all this stuff. This is all dealing with proportions. Yes. So, okay. This looks gnarly, and it is, but let's break it down for a second. When it comes to, we need to know how to find the standard deviation of a difference between two means. Because again, our either the interval we're looking for or maybe the null or alternative hypothesis is going to look at the difference between two means. Okay, and so we need to know what this standard deviation looks like, right? Either when I'm doing an interval and I'm building my my margin of error, I need to know what the standard deviation of that looks like so I could incorporate it into the margin of error. Or if I'm doing a hypothesis test like I have here, I would need to know the standard deviation of this guy when it comes time to find my test statistic, my t-statistic, and then next would be the p-value. So we got to know the standard deviation of this difference right here, all right, the difference between two means. Well, if you happen to somehow know the population standard deviation, then here it is. And actually, this is very familiar looking. Didn't we learn in 7.1 that the standard deviation of a sample mean is your standard deviation of the population over the square root of the sample size? Well, that is what they have here. All they've done is they've actually just included the sigma underneath the radical, but in order to account for the fact that it's supposed to be outside, they square it. So that essentially the square and the square root cancel each other, and really you're just looking at plain old sigma, and you've still got the square root of n down and below. All right, it's just that up top, technically these dudes cancel, and you're still looking at plain old sigma. So the format looks a little different than what we're used to, but it truly is the same thing. Now, very similar to proportions, if I'm looking at the difference of two means, I'm basically adding up their standard deviations. I'm adding up the total fluctuation they may have. Now, if this is the case, you would use z-statistics, all right, because you're using population standard deviation. More than likely, and in fact everything we're going to encounter in this course, we are going to have to use the sample standard deviation, right? So we are going to need to use t-statistics. All right, so in this case here, I'm going to use t-statistics. Using sample standard deviation. All right. Well, so the standard deviation itself isn't hard to find. That's it. However, when it comes to t-statistics, in order to find critical t-scores, there's a little thing called degrees of freedom. And when you're dealing with a one sample, degrees of freedom is easy. Isn't it normally just one less than the sample size, right? For one sample deal, isn't the degrees of freedom just one less than your sample size? That's easy to find. Not so easy here. That is the formula for calculating the degrees of freedom, okay? S sub 1 is the standard deviation of set 1, or data set 1, and N sub 1 is the sample size of data set 1. And the same for S sub 2 and N sub 2. So it's a gnarly looking formula. Now if you're doing it by hand, the conservative approach is just take the smaller of these two. Okay, so wouldn't this be the degrees of freedom for data set 1, and this would be the degrees of freedom for data set 2 individually? They say if you're doing this by hand, take the smaller of those two. And so it's not as accurate, but it's going to allow us to do it much more efficiently. Okay. When you plug it into StatCrunch, that's what StatCrunch is doing to calculate the degrees of freedom. All right, so doing it by hand, let's not forget that, because who wants to deal with that formula by hand? Okay, let's see. This is all, yeah, that's all proportion stuff we already did. So we skipped over this problem. Let's give this a shot. It says that 2 researchers investigated the reliability of test assessment. One group consisted of 30 students who took a proctored test. A second group consisted of 32 students who took an online test without a proctor. Remember, a proctor is someone watching you take the test. The 2 samples were taken independently and not paired or matched. Paired and matched, that's what we get into in the 10.4 stuff. We'll talk about that, okay? But right now these are not paired, they're not matched. So we have, again, we've got 2 groups here. We have a group that was proctored. So that means someone was standing in the room while the students took the test. And there is our sample size, there is the average test score, and there's the standard deviation of all the test scores. And then they're comparing that to a second group of students that were not proctored. No one was watching them take the test. Sample size, exam average, standard deviation. And I guess, the question one might have is, did this group do better? If they're not being proctored, is there a chance that cheating could have occurred? And is it more likely that those exam scores would be higher than the group that had someone in the room proctoring the exam? Okay. Now, what are we doing here? This says to estimate the difference between the mean scores of the 2 groups. So if you're trying to decide, is this a test or an interval? This is an interval because of that word estimate. We are looking for a number. We're looking for the difference between these 2 groups. So let's see. Maybe I'm just going to let, I'm going to use some little notation here. I'm going to let P be the proctored group. And how about N be the non-proctored group? All right, and so I want to look at the difference in the mean from the group P and the mean from group N, all right? And it doesn't really matter which one that goes first. That makes no difference at all. So you and I could do that differently. And when it gets time to do step 5, we will have the same interpretation, okay? So let's quickly try and run through these steps. Step 1 is state exactly what you're looking for, and because it's a confidence interval we're going to do, what's the level of confidence I want? We want the mean of the proctored group minus the mean of the non-proctored group. Or you could do it the other way around. It really doesn't matter, okay? The true difference in average test scores among the 2 groups. And let's just do this at good old 95% confidence level. Okay, let's see. Step 2 is name the procedure. Now I'm comparing 2 groups, so this is a 2. I'm looking for a mean, so it's talking about a 2 sample. And I am using sample standard deviation, so it's a T process, and I'm doing an interval, T interval. 2 sample T interval. All right. All right, 3. Independent, random, and large. And again, large enough, we mean for the sample means of the proctored and the sample means of the non-proctored to be normal or approximately normal. Okay, let's see. So independent, well, we can use the 5% rule because n equals 30 is less than 5% of all students that take a proctored exam. And same for the other one, n equals 32. Well, in the world there are many students taking non-proctored exams. So 5% is a very small sampling of those guys. So we'll treat as independent. Random, does it say random there? I don't see where if it says random, so if it doesn't say, then we would assume no. So it doesn't say. If it doesn't say, we can't assume it's random. Okay, if it doesn't say, then we cannot assume that it is random. Large enough? Well, each of these have a sample size greater than or equal to 30, right? So the number of proctored students was 30. That's greater than or equal to 30. And the number of non-proctored students was 32. Remember, for sample means, we just hope that our sample size is at least 30. So yes, large enough for the sample means of our proctored students and the sample means of our non-proctored students to be approximately normal. All right. Well, step 4 is where we do the thing. So let me write out the general form of my confidence interval. Again, it's the same form it's always been. It's your point estimate plus or minus the margin of error. It's just that this got a little uglier, that's all, but my point estimate would be the difference between these two groups. And again, it doesn't really matter which order you put it. I went ahead and wrote it first as the proctored group first minus the non-proctored group. It all comes down to how you interpret it on step 5. So my estimate would be the sample of the proctored group minus the average test score from the non-proctored group, that difference between those two exam scores, plus or minus the margin of error, which would be a t-score. Now what's the degrees of freedom here? Remember, back on the previous page, it said that instead of doing all of this, if you're doing it by hand, the conservative way to do it is take the smaller of the two individual degrees of freedom. So if my sample size is 30, that would be talking about 29 degrees of freedom. If the sample is 32, that would be talking about 31 degrees of freedom. We should take the smaller of those, so 29 degrees of freedom times the standard deviation, which is the sample standard deviation from the proctored group squared over the sample size of the proctored group, plus the same thing for the non-proctored group. All right, so it's ugly, but you know, if you can look past the ugliness of it and just realize, well, it's just a big formula that I'm plugging crap into, you know, you could chug through it. So anyways, let me just start plugging in these numbers here. This would be from proctored group, that's 70.29 minus 74.26 plus or minus this critical t-score. I have this written down, so I'm not going to go look for it, but we've looked at how to find t-scores, okay? So you could go consult your t-table. Find row where you have 29 degrees of freedom, and then again we're trying to block off the middle 95%, which puts 2.5% in each arm. Your T-table tells you right area, so you're going to look for the area of 2.5% in that row, 29 degrees of freedom, and it should give you this T-score. And plugging in those numbers for standard deviation, let's see, for proctored group this is 22.09 squared, and the sample size was 30. And for non-proctored it was 18.15 squared over 32. Yikes. Okay, so I could plug all this into the calculator, all right, and we would get the right answer. Let me make this look a little nicer, 18.15. Well, I hope we would get the right answer. As you can see, this is sort of a doozy, and there's definitely opportunities to plug it in incorrectly. So let me just run it through StatCrunch, because I want to show you that too, but let's let StatCrunch do the number crunching for us. So let me pull that up. Again, I would go to Stat. I'm doing T-stats on 2 samples with summary. I don't have data, I have a summary of my data. Now again, look at my confidence level interval down here. They put group 1 minus group 2. So to make it match what I had the proctored group minus the non-proctored group. So sample 1 needs to be the proctored group. So plugging in that information, for the proctored group, my sample size was 30. My sample mean was 70.29. And my standard deviation was 22.09. And for the non-proctored group, we had a sample mean of 74.26, a sample standard deviation of 18.15, and the sample size was 32. I said let's use 95% level of confidence. Let's see what we get. Here it is. My lower limit would end up being negative 14.3, and my upper limit would be 6.35. So let's say negative 14.3 to 6.4. So I would end up with negative 14.3 on the low end up to 6.4 on the upper end. This is by StatCrunch. And again, if you're using StatCrunch, don't feel the need to write out all this other stuff. Just go do it. And what I would do if I were presenting my work to turn it in, I would copy and paste that table, and that would be my step 4. So let's kind of think about how we're going to interpret this, because remember what this represents is this is representing the true difference in average scores from proctored tests versus non-proctored tests. So this is kind of interesting. We got a negative score on my lower limit. So think about what would it take for this to be negative. For this to be a negative number, what that means is that this second guy has got to be larger than the first guy, meaning the non-proctored group scored higher than the proctored group. Or in other words, the group that did not have someone supervising them scored higher than the group that did have someone supervising them. That would make this result have a negative score. Okay. Well, we get this positive score. The way we get that is if the proctored group, the group that had someone watching them, outscored or did better than this other group, the group that did not have someone watching them or proctoring the exam. Because then you would have a larger number here minus a smaller number, therefore giving us a positive result. So what this interval sort of suggests is that, yeah, sometimes maybe this group does better, but then again, maybe this group does better. Maybe they do the same. Maybe they score exactly the same, because wouldn't you notice that 0 has to be in between those two numbers? So maybe there is no difference whatsoever between the two groups. So that's kind of getting into the idea of a hypothesis test. We can now perform a hypothesis test on here if we wanted to. But basically, this shows me the difference in those exam scores. Sometimes one group does better than the other way around, it's kind of flipped. Again, when you get a negative score, it's because I'm taking away a number bigger than what this is. So that means the non-proctored group is doing better. But to get a positive score means the proctored group has to do better, because then when I take away something less, I'm left with a positive result. All right, well, it is what it is. Let's interpret it. Step 5. We could say that we are 95% confident that the true difference in mean scores between the two groups is between those two numbers. We are 95% confident that the true difference in mean test scores between the two groups is between negative 14.3 and 6.4. All right. Okay. Well, let's move on, and I think now we're going to have a hypothesis test coming up. So let's see. This we did in the last video. It dealt with proportions. There was a big hypothesis test on proportions. So yeah, now we're going to get into means, and they want us to write a hypothesis test for means. And they're using the same example, actually. 2 researchers investigate the reliability of a test assessment. One group consisted of 30 students who took a proctored test. Second group consisted of 32 students who took non-proctored test. The 2 samples were taken independently and not paired or matched. Okay. We wish to see if there's a difference in scores between the 2 groups. All right, so this is the same scenario, but we are going to perform a hypothesis test. So right now they're just having us practice writing null and alternative hypotheses. So again, I'm going to use the P for the proctored group and N for the non-proctored group. All right, so here, 2 questions here. The first one is saying, write a null and alternative hypothesis for this idea. We wish to see if there's a difference between the 2 groups. Okay, well, remember, a null hypothesis always uses equals. Always equals sign. And the alternative can use not equals, less than, or greater than. So the baseline assumption would be that there is no difference between the 2 groups, that they are equal to one another. So you could say that the one group equals the other group. But usually, remember, we like to think of it as bring this guy to the other side and get a 0 on the right. We prefer to compare it to a number. So I could take the mean of the proctored group minus the mean of the non-proctored group, and I would say that it is 0, that there is no difference, right? Because here's their difference, and I'm saying it's 0. There is no difference. Right? Or there is a difference, meaning if I were to subtract them, I get something that is non-zero. Okay? Because this just wants to know, is there a difference between the average scores of those 2 groups, the group that have a proctor and the group that do not. So the alternative would just be that there is a difference, that their difference is non-zero. Let's try this one. Here it says we wish to see if the mean score of the proctored test is lower than the mean score of the unproctored test. So we're trying to see if the mean score of the proctored test is lower than the non-proctored test. Okay? Right? Am I reading that right? The mean score of the proctored test, yes, is lower than the mean score of the non-proctored test. So again, my null is always equals, and it would just be under the assumption that they're the same. That there is no difference. The difference between them is 0. And the alternative is this idea for this particular problem. It's a different problem now. They want us to test a different idea. Well, again, I don't want to set it up like this. I'm going to bring it over here and bring it to this side to get it to compare to 0. So if I think that let's think about this for a second. If I think that the proctored test is lower, then that means if I were to take the average of the proctored test minus the average of the non-proctored test, I'm taking a small number minus a bigger number, So my result should be negative. Okay. But here's what you got to be careful of. Or, so this is perfectly fine. There's a perfectly good, legit way to do the test. However, what if I would have written them the other way? The non-proctored first, and then the proctored. The null would be that they're 0, that their difference is 0. There is no difference. And the alternative, if I were to write it this way, okay, oops, not equals. So let's think about this for a second. Now what I'm doing is if I think that the proctored test is lower, here's my small number, here's my bigger number, because I think the proctored test scores are smaller, then I've got a bigger number minus a smaller number. That would yield a positive result. This would be perfectly legit and fine to do as well. So you do have to be very careful about who is going first, and you have to be consistent. And there's not a right or wrong way to do it. You just need to be consistent and then be aware of which direction that inequality sign should go. All right? Okay. Let's try. I think they're going to have us do this on the next page, so let's see. Yep. So let's do the test. Okay. So this looks exactly the same. Okay, it looks like the exact same question. Researchers they're testing the reliability of or investigating the reliability of test assessment. You had 30 students who took a proctored test, 32 students who took a test without a proctor. They were independent and not paired or matched. Assume the conditions for inference procedure are met. Ooh, I like that. That is saying step 3 is taken care of. Though I would have jumped that anyways because we already proved step 3 for this scenario on a previous problem. So step 3, done. Okay. Don't do that on a test. Make sure you do the whole thing, but we already did it, so we're going to save a little time here. Look at this. They're saying use alpha to be 1%. That's pretty low. Remember we talked about in 9.3 that you don't usually want to go that low because if alpha is too low, it becomes hard for the null to reject, right? It becomes hard to reject the null because your limbo bar is so low, and you might potentially make a type 2 error, which would be to not reject the null when you really should be getting rid of it. So I would always default to 5% personally, but let's go with what they say. Same exact data here. So let's go with steps 1. What do they want us to test? Use 1% level of significance to test if the non-proctored group is significantly higher than the proctored group. So the average of the non-proctored group being higher than the proctored group. Okay, which is the same thing as saying the proctored group is less than the non-proctored group. It does not matter which way you think about it. You just got to make sure that you pick a way and are consistent with it. So my alternative would be that there is no difference, that the difference between the groups, I guess I got to pick one. It doesn't matter. I'll go with that guy. Okay, I'm going to use StatCrunch anyways to help me with this, so I'm just going to go with that. The null alternative would be that the, you know what? I think I did it the other way in my confidence interval, so I'm just going to go with this because I think that's the order I had in my confidence interval. But it makes zero difference whatsoever, okay, guys? Anyways, I want the mean of the proctored group minus the mean of the non-proctored group to have no difference. Their difference is 0. The alternative to that is that the mean of the proctored group minus the mean of the non-proctored group. Now let's think about this. We think, or we're trying to test, that the non-proctored group is higher. So this number is higher than this number. Okay, if it's higher, then I'm taking a small number and I'm subtracting a bigger number, which would leave me with a negative result. All right. You could also see it here. If you just bring this over here, you're left with this minus this is less than 0. I'm going to erase this so we don't get confused with what it's saying. And they told me that alpha is 0.01. All right, this is a 2-sample t-test. Step 3, done. Oh, I like that. That feels good. Step 4, we need to do the thing. So I'll go ahead and write it out. I mean, I won't do it all. I won't pull up the table, but I'll get it set up, and then we'll pull out StatCrunch. So again, for a hypothesis test, the first thing you'll do is you'll find your test statistic, which hasn't changed. It's still going to be, and again, in this case, it's a t-test, but it's going to be what you observe minus what is claimed over the standard deviation. That's how every test statistic is gone. Okay, so what I observe is the difference between this sample and this sample. Let me make sure I go with my correct order. Proctored group first and then non-proctored group. So that would be 70.29 minus 74.26. That was the proctored group first, and then this guy's second. And just because that's the order I stated in my hypotheses. Minus the claim. Well, the claim is that there is no difference between them. And what we just saw on the previous page is the standard deviation basically adds up the standard deviation of each of these. It's the standard deviation of the proctored test squared over the sample size of that test or sample. And then it's going to be the standard deviation of the non-proctored group squared over that sample size. That is my t-score. Now I have it written down that that's negative 0.770. We'll verify with StatCrunch, and maybe that's where I got it, was from StatCrunch instead of throwing that all in the calculator. But you could, and then the next thing you would do after that is you'd say, well, I need my p-value, and that would be the probability of getting a t-score. What do I want? Less than, right? Yep, because my alternative wants less than, so do I. The probability of getting a t-score less than that, which if you're using the t-table is sort of inconvenient. Don't forget that by symmetry, this is the same as the probability of getting a t-score greater than positive 770, which that's what I would use on my t-table, because our t-table is designed to tell area right of scores, not area left of scores. Okay. But and depending on how low that probability is, again, what that probability is it's the likelihood or the probability of getting the results we got, assuming that there should be no difference in the scores. Right? If the null is true and there's no difference in the scores, then the p-value represents the probability that we would get that difference in scores. And if it's really unlikely, if it's very, very low probability that we would get those, but somehow we did get them, that seems to suggest that the null was incorrect and that there actually is a difference between them. So I'm going to do it all on StatCrunch though, and just get those numbers that way. So I want a, come on now, t-stats, because we're doing means with sample standard deviation. I got two samples. I have summary. Again, look at my hypotheses. They put group 1 minus group 2, right? The mean of group 1 minus the mean of group 2. In my problem, I'm doing the proctored group minus the non-proctored group. So sample 1 better be the proctored group. It doesn't matter, but make sure you're consistent and make sure you're plugging in the right order so that your results aren't backwards. Okay, so for group 1 needs to be the proctored group information. They had a sample mean of 70.29, sample standard deviation of 22.09, and a sample size of 30. My non-proctored group had a mean of 74.26, standard deviation of 18.15, and a sample size of 32. Okay. The pooled variances, that, where did we talk about that? Oh, we talked about that in the hypothesis test in 10.3 for proportions. you know, it's not going to make a big difference. So you can pool the variances or you cannot. And maybe I'll show you what that means, or show you the difference in them. But if you remember, what that means is that let me flip back to the notes. When doing the standard deviation right here, whenever your null hypothesis assumes that they are equal, that there is no difference in the two numbers, remember, they don't treat them as equals here, or as two different things here. What they do is they just combine they basically add up the average scores here for both of these and divide by both sample sizes together. So it made a little more sense with the one we did in the last video. They were comparing men and women and some difference between them. Well, because the difference was claimed to be 0, no difference between the men and the women, they pooled the values and basically gave us the standard deviation based on people, not men and women individually. So you can pool them, you cannot. I mean, I guess the claim is that they are the same, so I'll go ahead and pool them. But I'll show you that there's not going to be a big difference in them. The claim is that there's no difference, and we are testing that there is a difference and that it's less than, I believe. Less than, yes. Okay, let's see what we got. All right, with the pooled variances, so with pooled variances, here was my test statistic, negative 0.775. I said 0.770, right? And there's our p-value, 22%. Let me go back and unpool it. So take a look at the p-value and t-stats. Let's see how the p-value and t-stat change when I unpool it. Really, really close still. Okay, still 22% and change, still negative 77 point. This is closer to mine actually, which actually makes sense because the one I wrote, I didn't pool them, right? These are not pooled, okay? I'm treating them separately. All right, anyways, I got a p-value of over 20%, so that's large. So this p-value is approximately 0.222. I'll just go with that one. All right. It is well above my alpha, right? My level of significance. So what this means is that this is the likelihood of me getting those results. If the claim is true and there really is no difference in the average test scores between these two groups, then the probability of me getting this difference in scores, because there is a difference here, the probability of me getting that difference is 22% chance for that to happen. So that's not an anomaly. That's not something that's abnormal. That was fairly darn likely to happen. So it means that the fact that there's a difference in the values here isn't enough to be significant enough for me to think that there's actually no difference in the true average. Okay, it wasn't statistically significant. Now, if this was like 0.0002, well, that all of a sudden is very unlikely to happen, very unlikely to hit, but we did hit it. And so that makes us think that it's not like we were lucky and we're just, we're pulling things off that are really unlikely to happen. It makes us think that the original claim is wrong. But not in this case. Since my p-value is higher than alpha, we fail to reject the null. So in other words, the data does not suggest that one group scores lower than the other, okay, or the one group scores higher than the other. I'll try and say it how they did. The data does not suggest that the proctored group would score better than the non-proctored group. Because remember, if the proctored group, that the non-proctored group scores higher than the proctored group. If the non-proctored group scored higher than this group, that's how we get a negative answer, because you've got a small number minus a big number. So the data does not suggest the non-proctored group scores higher than the proctored group. All right, done. Now, there's one more problem on here. I decided just to skip it, sort of out of pure laziness. Sorry, but first of all, when you read this thing, I bet we don't have an idea of what's going on with it, and that's fine. It says weighted alpha is a measurement of risk-adjusted performances of stocks over a period of a year. I don't know about you, but that's over my head. You know what I mean? I'm not into investing and things like that, so that doesn't speak to me, okay? That doesn't mean I couldn't do the hypothesis test. If you give me data and ask me to perform a test, yeah, I could do that for you, no problem. I don't have to understand what it means. I can look at those numbers and tell you if one is bigger, one data set is bigger than the other, okay, statistically wise. So you don't have to understand the problem to do it, okay? It says, is there sufficient evidence of a difference in weighted alpha between the two regions, you know, northeast and west? So basically it's asking, you know, from this data set there would be a mean of the northeast region and there would be a mean of the west region. There would be sample means, sorry, from here. That would be our point estimate, really. We would use those point estimates, but we want to see if there's a difference in the true mean values between those. So like my null and alternative would just be, my null would be that there is no difference between the average weighted alpha score in the northeast compared to the west. That those two averages are 0. The difference between those averages is 0. There's no difference. The alternative, you know, it doesn't suggest or ask whether or not one is bigger than the other. It just says, is there evidence of a difference between them? So the alternative would just be that there is some sort of difference between them, that the difference is not 0. So the lazy factor of why I'm skipping it is because I can't copy and paste this data from my OneNote. So I would have to go, what I would do is I would go to OneNote and I would type in all these data values. All right, and then when I go to OneNote and I go, so I would have a bunch of data values in this column for the northeast people, and then I would have a bunch of data values in here for the west coast. And when I go to t-stats, try it again, try it. My pen won't work well. Hold on, let me get my keyboard mouse. When I go to t-stats, 2 samples, this time I would click data because I would have all this data loaded up. Now when I do that, it would say, okay, which column is sample 1 in? And I would tell it, well, I don't have anything in there, but I would tell it either variable 1 or variable 2. And then I would tell it where to look for the next set of data, and then I would have it, I would do my test right here. All right, so it's even easier to set up than with a summary because you literally just need to tell it which column to look at. Here's where you get, this column gives you your first set of data, this column gives you your second set of data. Again, if you had data loaded up into here. And again, I can't copy and paste it. I don't know what that just did. Can't copy and paste it out of here. So I'm going to hope and bank that this video went okay for you and you can go off this example for the hypothesis test, and we'll do some more in class. But yeah, I'm going to end it right there, guys, okay? And we will do some problems together now.